Good morning, welcome to class. Today we're going to have a look at the second lesson of chapter 9. We're going to talk about diffraction and interference of water waves. Have you ever noticed how people relaxing at the seashore spend so much of their time watching the ocean waves moving over the water as they break repeatedly and roll onto the shore? Water waves behave similarly to other kinds of waves in many ways. So here, figure 1 illustrates one characteristic behavior of waves. When a part of the wave enters through a narrow opening, the section of the waves that gets through acts as a source of new waves that spread out on the other side of the opening. And the waves from the two sources combine in specific ways. We will learn about these characteristic behaviors of waves in this section. Okay, so now let's have a look at the concept of diffraction. If we observe straight wave fronts in a ripple tank, we can see that they travel in a straight line if the water depth is constant and no obstacles are in the wave. If, however, the waves pass by an edge of an obstacle or through a small opening, the waves spread out. Diffraction is the bending of a wave as a wave passes through an opening or by an obstacle. The amount of diffraction depends on the wavelength of the waves and the size of the opening. So here in figure 2a, an obstacle diffracts shorter wavelengths slightly. And also you can see in figure 2b, the same obstacle can diffract longer wavelengths more. Okay, so in a summary, the diffraction is the bending and spreading of a wave when it passes through an opening, dependent on the size of the opening and the wavelength of the wave. So although diffraction also occurs for sound and light waves, we will study the phenomenon first for water waves because their long wavelength allows for easier observation of the effects of diffraction. Okay, here in figure 3a, we can see a wave encountering a slit with a certain width W. In figure 3b and figure 3c, the width of the opening is the same, but the wavelength of the incident waves has changed. Notice how the amount of diffraction changes. Therefore, as the wavelength increases, but the width of the slit does not, the diffraction also increases. In figure 3a, the wavelength is approximately 1/3 of W. Notice that only the part of the wavefront that passes through the slit creates a series of circular wavefronts on the other side. In figure 3b, the wavelength is about half of W, which means that significantly more diffraction occurs. But areas to the edge exist where no waves are diffracted. In figure 3c, the wavelength is approximately 2/3 of W, and the sections of the wavefront that passes through the slit are almost all converted to circular wavefronts. So what happens if you change the width of the slit but keep the wavelength fixed? As figure 4a and figure 4b show, as the size of slit decreases, the amount of diffraction increases. If waves are to undergo more noticeable diffraction, the wavelength must be comparable to or greater than the slit width, or lambda is greater than or equal to W. So here lambda stands for the wavelength, and W stands for the width of the slit. For small wavelengths, such as those of visible light, you need to have narrow slits to observe diffraction. Figure 4c here shows what happens to the diffraction pattern when the wavelength decreases, but the size of the slit does not change. Okay, in a summary, in figure 4, A and B are the cases as the size of slit decreases, diffraction increases. Where in figure C, it shows the case that with a shorter wavelength and no change in the size of the opening, there is less diffraction. So the relationship between wavelengths, width of the slit, and extent of diffraction is perhaps familiar for sound waves. We can hear sounds through an open door, even if you cannot see what is making the sound, right? Primary reason that sound waves diffract around the corner of the door is that they have long wavelengths compared to the width of the doorway. Low frequencies, or the longer wavelengths of the sound, diffract more than high frequencies, the shorter wavelengths of the sound. So if a sound system is in the room next door, you are more likely to hear the lower frequencies or the bass. Okay, next let's have a look at a sample problem in which we'll learn how to solve problems relating to diffraction. Okay, now let's consider this sample problem here. We are given a figure here, figure 5. Can you determine and explain the the difference between the diffractions observed in figure 5a and figure 5b? Okay, I'll give you 5 minutes to consider this question here. Then after that, we'll have a look at the solution together. All right, let's have a look at the solution here. So what is the difference between figure 5a and figure 5b? Okay, so for figure 5a, we can find the ratio between the wavelengths and the width of the opening, which is lambda over WA. And this gives us 0.5 centimeters over 2 centimeters. And this ratio is 0.25. Therefore, we can see the ratio between the wavelengths and opening of the width, the width of the opening is less than 1. On the other hand, for figure 5b, if you find the ratio between the wavelength and the width of the opening, that number is 1, right? Since the ratio in figure 5a is less than 1, little diffraction occurs. Since the ratio in figure 5b is 1, more noticeable diffraction occurs. So that's the difference between these two cases. All right, next, let's have a look at another concept, which is called interference. When two waves cross paths and become superimposed, they interact in different ways. This interaction between waves in the same medium is called interference. We experience interference when we listen to music and the other types of sound. For example, sound waves from two speakers may reach the listener's ears at the same time, as illustrated in figure 6 here. If the crest of one wave coincides with the crest of the other, then the waves are in phase and combine to create a resultant wave with an amplitude that is greater than the amplitude of either individual wave, resulting in a louder sound. This phenomenon is called constructive interference. On the other hand, for two waves that differ in phase by 1/2 of the lambda, which is 1/2 of the wavelength, which is shown here in figure 6c. The crest of one wave coincides with the trough of the other wave. This corresponds to a phase difference of 180 degrees, right? So in this case, the two waves combine and produce a resulting wave with an amplitude that is smaller than the amplitude of either of the two individual waves. This phenomenon is called destructive interference. Okay, so let's revisit some of these important concepts here. First, interference is the phenomenon that occurs when two waves in the same medium interact. Next, constructive interference means the phenomenon that occurs when two interfering waves have displacement in the same direction when they superimpose. Next, destructive interference means the phenomenon that occurs when two interfering waves have displacement in opposite directions where they superimpose. Where coherent means composed of waves having the same frequency and fixed phases. Okay, the following conditions must be met for interference to occur. First, two or more waves are moving through different regions of space over at least some of their way from the source to the point of interest. Second, the waves come together at a common point. Third, the waves must have the same frequency and must have a fixed relationship between their phases such that over a given distance or time, the phase difference between the waves is constant. Waves that meet this condition are called coherent. So as we just discussed here, coherent means composed of waves having the same frequency and fixed phases. So here, figure 7 shows water waves that are interfering. In figure 7, 2 point sources have identical frequencies. The sources produce waves that are in phase and have the same amplitude. Successive wavefronts travel out from the two sources and interference with each other. Constructive interference occurs when a crest meets a crest, or when trough meets a trough. Destructive interference occurs when a crest meets a trough, resulting in zero amplitude. So let's have a look at the pattern here, shown in figure 8. Symmetrical patterns spread out from the sources, producing line locations where constructive and destructive interference occur. A node is a place where destructive interference occurs, which is here. Node is a place where destructive interference occurs, resulting in zero amplitude, or a net displacement of zero. So here, as shown in figure 8, the interference pattern includes lines of maximum displacement caused by constructive interference, separated by lines of zero displacement caused by destructive interference. The lines of zero displacement are called nodal lines. Okay, let's revisit the two concepts here. A node is a point along a standing wave where the wave produces zero displacement, whereas nodal line means a line or curve along which destructive interference results in zero displacement. Which is here. These are called nodal lines. Okay, so when the frequency of the two sources increases, the wavelength will decrease, right? Which means that the nodal lines come closer together and the number of nodal lines increases. When the distance between the two sources increases, the number of nodal lines also increases. The symmetry of this pattern does not change when these two factors are changed. However, if the relative phase of the two sources changes, then the pattern shifts. As shown here in figure 9, but the number of nodal lines stays the same. In figure 9a, the sources are in phase, but in figure 9b, there is a phase difference of 180 degrees. Okay, any questions? Okay, if you don't have any questions, you can take a 10 minutes break, and after that, we'll talk about the mathematics of the two-point source interference. Okay, good. Let's get back to work. Next, let's talk about the mathematics of two-point source interference. Well, actually, we can measure the wavelengths using the interference pattern produced by two-point sources and develop some mathematical relationships for studying the interference of other waves. Here, figure 10 shows an interference pattern produced by two-point sources in a ripple 10. The two sources marked as S1 and S2, separated by a distance of 3 wavelengths. The vibrating are vibrating in phase. The bisector of the pattern is shown as a white line perpendicular to the line that joins the two sources. We can see that each side of the bisector has an equal number of nodal lines, which are labeled with N1 and N2 on each side. A point on the first nodal line, N1, on the right side is labeled P1. And a point on the second nodal line, N2, on the right side is labeled as P2. The distances P1S1, P1S2, P2S1, and P2S2 are called path lengths. If we measure the wavelengths, we will find that P1S1 equals 4 lambda, and P1S2 equals 7/2 lambda. The path length difference, which is noted as delta S1, on the first nodal line is equal to delta S1 is the absolute value of the difference between P1S1 and P1S2, which gives us delta S1 equals a half of the wavelength times lambda here. This equation applies for any point on the first nodal line. We can use the absolute value because only the size of the difference in the two path lengths matter, not which one is greater than the other. A node can be found symmetrically on either side of the perpendicular bisector. The path length difference, delta S2, on the second nodal line is equal to delta S2 is the absolute value of difference between P2S1 and P2S2. And this gives us delta S2 equals 3 half wavelengths, or 3/2 lambda. Extending this to the nth nodal line, the equation becomes delta Sn equals the absolute value of the difference between Pns1 and Pns2. And this gives us delta Sn equals n minus 1/2 times the wavelength lambda, where Pn is any point on the nth nodal line. Thus, by identifying a specific point on the nodal line and measuring the path length, you can use this relationship to determine the wavelengths of the interfering waves. This technique will not work if the wavelengths are too small or the point P is too far away from sources, because the path length difference is too small to measure accurately. If either or both of the conditions apply, we need to use another method to calculate the path length difference. Okay, so let's have a look at this graph here, this figure here, figure 11. For any point P, the path length difference is AS1, as shown here in figure A. We have the absolute value of Pns1 minus Pns2 equals AS1. Right? In this triangle here. When Pn is very far away compared to the separation of the two sources, D, then the lines PNS1 and PNS2 are approximately parallel, right? You can imagine that. And Pn is very far away compared to the separation of the two sources, which is here D. Then you can imagine PNS1 and PNS2 are approximately parallel, which is shown here in figure 11b. So in figure 11b, the lines AS2, S1, S2, and AS1 from the right-angled triangle, which means that the difference in path length can be written in terms of angle theta n, which is here. We have sine theta n equals AS1 over D, right? This is according to definition of trigonometric ratio. Sine theta n equals AS1 over D. So we can rearrange this equation to D sine theta 1 equals AS1. However, on the previous discussion, we established that AS1 here, AS1 is the difference, the absolute value of the difference between PNS1 and PNS2, right? So this is our AS1, which equals n minus 1 over 2 lambda, which is here. Okay. Combining this with the expression for AS1 in terms of sine theta 1, this gives us the following relationship. Sine theta n equals n minus 1 over 2 times lambda over d. The angle for the nth nodal line is theta n. The wavelength is lambda, and the distance between the source is d. Using this equation, we can approximate the wavelength for an interference pattern. Since sine theta cannot be greater than 1, it follows that n minus 1/2 times lambda over d cannot be greater than 1. The number of nodal lines on the right side of the pattern is the maximum number of lines that satisfies this condition. By counting this number and measuring d, we can then determine an approximate value of the wavelength, right? For example, let's consider this example here. If d is measured to be 2.0 centimeters and n is 4 for a particular pattern, then put all the values in. We have 4 minus 1/2 times lambda over 2.0 centimeters is approximately 1, right? And this gives us the wavelength lambda is approximately 0.57 centimeters. So using this way, we can approximate the wavelength. Okay, although it's relatively easy to measure theta for water waves in a ripple tank, for light waves, the measurement is not as straightforward, right? Because it's not very easy to measure the light. The wavelength of light is very small, and so is the distance between the sources. Therefore, the nodal lines are close together. We need to be able to measure sine theta without having to measure the angle directly. Assuming that a pair of point sources is vibrating in phase, we can use the following derivation. For point P, that is on the nodal line and is distant from the two sources. The line from Pn, which is here, this is our Pn in this case. Line from Pn to the midpoint of the two sources, which is denoted by PNC, can be considered to be parallel to PNS1. This line is also at right angles to AS2. The triangle PNBC in figure 12 is used to determine sine theta prime. In this, D is the distance between the sources. Xn is the perpendicular distance from the right bisector to the point Pn, right? L is the distance from Pn to the midpoint between the two sources. And N is the number of the nodal lines. Therefore, we have the following relationship here. Sine theta n prime equals xn over L. Okay, can you see the relationship here? This is your theta n prime. Sine theta n prime equals the opposite side xn over the hypotenuse L. Okay, so figure 3 here on the left side is an enlarged version of the triangle with base CS2 in figure 12. Since we have sine theta n equals n minus 1/2 times the wavelength lambda over d. And since the right bisector CB is perpendicular to S1, S2, we can see in figure 13 that theta n prime is equal to theta n. Okay, so we can say that x over L equals n minus 1/2 times lambda over d. We can have this relationship here. Okay, I'll give you some time to have a look at these two formulas, and then we'll consider a sample problem in which I'll demonstrate how we can solve problems involving two-dimensional interference. Okay, next let's have a look at a problem here. The distance from the right bisector to a point P on the second nodal line is in a 2-point interference pattern is 4.0 centimeters. The distance from the midpoint between the two sources, which are 0.5 centimeter apart, to point P is 14 centimeters. So based on this information, first, can you calculate the angle theta2 for the second nodal line? Then calculate the wavelength. Okay, you can refer to the diagrams here and the equations we derived from the mathematical analysis in the interference in 2 dimensions here. Okay, let's have a look at the solution together. In question A, we are given that n equals 2, right? And x2 equals 4.0 centimeters, and L is 14 centimeters. So we can directly use the formula sine theta n equals xn over L. So in this case, we have sine theta 2 equals x2 over L. Therefore, theta 2 must be arc sine theta of x2 over L. To put all the values in, we can solve theta 2 is approximately 17 degrees. So the angle of the second nodal line is 17 degrees. Okay, as to question B, we have another relationship. We can use this formula here, right? To evaluate wavelength lambda. So according to the formula, we have xn over L equals n minus 1/2 times lambda over d. So in this case, n equals 2. So we have lambda equals x2 times d divided by 2 minus 1/2 times L. This gives us the wavelength lambda is approximately 0.095 centimeter. So if you want to keep two significant figures, you should write the wavelength is 9.5 times 10 to the power of -2 centimeter. Any questions? Okay, if no question, let's consider another simple problem here. This problem shows how we can determine the wave pattern properties using differences in path lengths. Okay, so we have two identical point sources, which are 5.0 centimeter apart in phase and vibrating at a frequency of 12 Hertz. They produce an interference pattern. A point on the first nodal line is 5 centimeters from one source and 5.5 centimeters from the other. Question A, can you determine the wavelength according to the given information here? Question B, determine the speed of the waves. We call that the speed of a wave equals the wavelength times the frequency, right? So if you know the wavelength times its frequency, which is a given information, then we can find the speed of the wave. So the key is to solve the wavelength of this wave. Okay, I'll give you 5 minutes to have a look at this question. Then we'll have a look at the solution together. Okay, let's have a look at the solution here. In question A, we are given the following information. N equals 1, right? And P1S1 equals 5.5 centimeters. P1S2 equals 5.0 centimeters. And D is 5.0 centimeters. So according to the formula, PNS1 minus PNS2 equal the absolute value of difference between PNS1 and PNS2 equals n minus 1 over 2 times lambda. So in this case, n equals 1. So we have the absolute value of difference between P1S1 and P1S2 equals 1 minus 1/2 times lambda. Therefore, we can solve lambda to be 1.0 centimeter. So the wavelength is 1.0 centimeter. And if you know the wavelength and also the frequency of the wave, then we can find its speed, right? Because for any wave, the speed equals lambda times f, which is 1.0 centimeters times 12 hertz, which gives us 12 centimeters per second. So the speed of the wave is 12 centimeters per second. Okay, have a look at this solution here. Do you have any questions? If no questions, that's the end of today's lesson. I'll see you next time.